recall that the inverse of the exponential function, b to the x, is the logarithm function log base b of x. So be sure to say it that way. Say log base b of x. The word of is there to remind us of a function. We have a function. Similarly, this f, left parenthesis x, right parenthesis, that is pronounced f of x. Without the of, what happens is people mistakenly think of multiplication. But there's no multiplication going on here. Another thing is that b to the x is not equal to log base b of x. These are two different functions that are related to each other. Okay, these two functions are not the same. So it would be incorrect to replace log base b of x with b to the x. I've seen that happen. I've seen people take log base b of x that's just sitting randomly in a problem. They'll just turn that into b to the x. Well, they're not the same. Just they're related to each other. The two pictures are diagonal flips of each other, meaning that they're not the same picture. Right? So these two functions are related in that they're inverses of each other. Also, ln of x is shorthand notation for log base b of x. So if you ever see ln of x and you want to write log base e of x instead, that's fine. Just note that ln, or natural logarithm, it's just a shorthand notation. And say it that way, ln of x. Again, without saying the of, sometimes people think ln times x. I've even heard people say aloud ln times x. But there's no multiplication going on. Okay, again, the inverse of b to the x is log base b of x. So the inverse of one function is the other function. So the two graphs are diagonal flips of each other. Over here you have the picture for b to the x. Over here you have the picture of log base b of x. So the picture on the left is y equals b to the x, at least the case when b is bigger than 1. And then the picture on the right is log base b of x. So since the range of the exponential function is 0 to infinity, excluding 0, then the domain of the inverse function, the domain of the logarithm function, is 0 to infinity, excluding 0. This fact comes up a lot, the fact that the domain of logarithm is 0 to infinity. So domain, remember, is about the inputs. Like, what can be the input? What could we plug in here for x? It has to be something bigger than 0. Okay, so, typo, this should say parenthesis 0 comma infinity is the domain of every logarithm. Or in other words, the input to any and every logarithm must be positive. So let's summarize from last time. Finding the domain of a function. Now there's three things to keep track of. So two old things. We need the contents inside a square root to be greater than or equal to 0. We have to avoid denominator equaling 0. And the new thing is that we want the input to a logarithm to be bigger than 0. This all just goes back to what we just saw, that the input to logarithm has to be bigger than 0, or that the domain of the original logarithm is 0 to infinity. So let's do a sample problem. To find the domain of f of x equals ln of 2x plus 10 all over x squared minus 5x plus 6. Now this ln, it is a logarithm. Ln is just, remember, shorthand notation for log base e. So this is a logarithm. It just happens to be log base e. So the input to this logarithm, which is 2x plus 10, that needs to be bigger than 0. So we want 2x plus 10 to be bigger than 0. We also need to avoid the denominator equaling 0. So avoid x squared minus 5x plus 6 equals 0. So this 2x plus 10 greater than 0, that turns into we want x to be greater than negative 5. And then if you solve the equation x squared minus 5x plus 6 equals 0, there are two values of x to avoid. We need to avoid x equals 2, and we have to avoid x equals 3. So if we put that all together, the domain is going to be parenthesis negative 5. We can't have negative 5 itself. It's x is greater than negative 5. So parenthesis negative 5 comma 2, parenthesis, avoiding 2, union parenthesis 2 comma 3 parenthesis, union parenthesis 3 comma infinity parenthesis. Now, what about this 2 comma 3? It's here just as a reminder that don't leave out the interval 2 to 3. So yeah, 2 and 3 happen to be consecutive integers, or integers that are right next to each other, but that shouldn't change the fact that it's okay for a number between 2 and 3, like 2.731. That's okay to use as an input. That's an input to this function. So sometimes people only have the first and the third interval here. We also need this middle interval from 2 to 3. Okay, now let's make this active. Here's the graph of the logarithm. This is the diagonal flip of the exponential function, like for instance ln of x. So this is log base e of x, but all the log functions have this general shape to them. And then over here on the right is y is equal to root x, y is equal to square root of x. So if you'd like, the pictures here are rather small and you can't really zoom in, here very well and so on. For a better view, go to Desmos. Type both of these in. Interactive question. Identify at least 4 similarities or differences between the graph of the natural logarithm function and the graph of the square root function. Just a reminder, the key thing, the important thing from last time, you'll see this a lot. You have to be familiar with the definition of logarithm. You won't have time to just look it up every time. You've got to get yourself very familiar with this. And we've stated it twice. A to the k equals n if and only if log base a of n equals k. Another way to state it, u to the z equals r if and only if log base u of r is equal to z. So you'll notice the base is the base, right? So that's why even in the phrasing we say like log base a of n. So that base a, okay? Base a both in the exponent side equation and base a in the log. Then you'll notice the other two variables were n and k, and in one equation n is isolated by itself on one side of the equation, and in the other equation k is by itself on one side. That's how you remember it, yeah? So if the base is the base, there's only two more variables, and in one of the equations one of the variables is isolated, and in the other equation the other variable is isolated. So notice here like r is by itself, and then in the other equation z is by itself. That's how you remember this. So based on the definition, we went through this last time, but log base 3 of 81 is simplified by asking 3 to the what is 81? And, well, that what is 4, yeah? So in answer to the question, log base 3 of 81, that's equal to 4. Okay, here's another one. Log of 1000. Now the base is missing, but when the base is hidden, it's really a hidden 10. So in other words, the question here, it's really log base 10 of 1000. And just like before, just like the question we're looking at, ask yourself, how do we reword the question? Turn it into this format, yeah? Once you've turned it into the new format, the question's actually not so bad to answer. But if you don't turn it into that format, then we've got nothing to go off of here. So turn this question into 10 to the what is equal to 1000, and, well, that is 3. Yeah. So log of 1000, or for more clarity, log base 10 of 1000, that's equal to 3. Now let's just note some kind of incorrect type notation I've seen people do is people write log base 10 of 1000, but then they'll write like equals as if next step, equals 10 to the x equals 1000, and I think they're writing the x to mean like, okay, that's the what, but let's say that that's equal to 3. I mean, there's all kinds of things going on here. 1000 isn't equal to 3. I mean, there's lots of incorrect notation going on. So just off to the side, you answer the question, 10 to the what is equal to 1000, and then whatever that what is reported as the answer. You notice the notation here, trying to model this, is log base 10 of 1000, just literally just equals 3. All right, so just one other application I want to bring up is, log base 10 of 100 equals 2, and log base 10 of 1000 equals 3. That was the one we just computed. Log base 10 of 10,000 is equal to 4, right? Because 10 to the what equals 10,000, and that what would be a 4. Now, with one kind of minor detail missing above, this is actually basically the idea behind reporting earthquakes on the Richter scale. So an earthquake with a shaking intensity of 100, over here, is reported as a 2.0 earthquake, and an earthquake with a shaking intensity of 1000 is reported as a 3.0. An earthquake with a shaking intensity of 10,000 is reported as a 4.0. So I say this because a 4.0 earthquake, if you ever hear about this in the news, a 4.0 earthquake isn't twice as bad as a 2.0 earthquake. Actually, if you look at 10,000 divided by 100, you'll get the number 100. So actually a 4.0 isn't twice as bad, it's 100 times as bad. It's 100 times as shaky. So the thing is, the USGS reports using this log scale. It might seem funny, but this is called a log scale. Why report numbers like 2.0, 3.0, 4.0? Why not just report it as is, like 100, 1,000, and 10,000? The issue is because providing the actual shaking intensity is not very helpful for people. Because the actual numbers are too big to comprehend. Do you want the news to report, who wants to compare like one with, I didn't even count how many zeros versus this one with that many zeros. Like, it's just, when the numbers get that big to report on the news, it's just not useful for people to comprehend what's going on. So that's why instead of reporting the actual shaking intensity, that shaking intensity number, it's fed through as the input to a log base 10, and just the output of the log base 10 is reported as as what we say the Richter scale is for an earthquake. It's not the only place this log scale is used. Decibels for how loud sound is. I mean, there's actually lots of applications for this. And so as a general application of logarithms, when the numbers you need to report on are big, are way too big to comprehend, people usually feed this into a log base 10. So the number reported is a result of applying a logarithm. And really what's going on is if we look at the definition of logarithm, here it is stated again, okay, the value that's reported, so it's the output of the logarithm, like here represented by a z, that's actually the exponent. You look at here, it's u to the z equals r. So what's getting reported is just the exponent itself. The value of a logarithm in the end is actually just the missing exponent. Yeah. So that's helpful. Is instead of reporting numbers so big, you're just saying 10 to the what. Just reporting what that what is makes it just much easier to comprehend what's going on.